Okay, the objective here is to derive the equations of motion for the inverted pendulum. So remember, we have a cart of mass m1, and then a mass m2 on a point mass m2 on a massless rod, length L, and then this angle here is theta, and the position of the cart will be x. Okay, so the generalized coordinates are q1 is equal to x and q2 is equal to theta. The generalized forces, so we're assuming an applied force of F and then a damping that opposes the motion with a damping coefficient of B. So the generalized forces will be tau 1 is equal to F minus B x dot, and tau 2 is equal to 0. There are no applied forces on the pendulum. Okay, now we derived in previous lectures the kinetic energy as K is equal to 1/2 m1 plus m2 x dot squared plus 1/2 m1 L squared theta dot squared plus m1 L x dot theta dot cosine theta, and the potential energy as P is equal to P naught minus m1 GL 1 minus cosine of theta. Therefore, the Lagrangian is L is equal to K minus P 1/2 m1 plus m2 x dot squared plus 1/2 m1 L squared theta dot squared plus m1 GL x dot theta dot cosine theta minus P0 plus m1 G 1 minus cosine of theta. Okay, so the equations of motion then are given by the Euler-Lagrange equations, which in this case are d dt partial of L with respect to q1 dot minus partial of L with respect to q1 is equal to tau 1, where q1 is equal to x, and ddt of partial of L with respect to theta dot minus partial of L with respect to theta is equal to tau 2, where q2 is equal to theta. Okay, so when we need to derive some of these quantities. So if we look at the previous equation, then we have that the partial of L with respect to x dot is going to be equal to m1 plus m2 x dot plus m1 L theta dot cosine of theta, and that implies, and then recognize that x dot is a function of t, as is theta dot, as is theta. Therefore, when we take the time derivative of partial of L with respect to x dot, we have to use the chain rule. We get m1 plus m2 x double dot, and then we use the chain rule for this formula to get plus m1 L theta double dot cosine of theta, and then minus m1 L theta dot squared, because theta here is being differentiated sine theta, and the derivative of cosine is negative sine, giving us the negative sign here. Okay, and the partial of L with respect to x is equal to 0, since x does not appear in the Lagrangian all by itself. Similarly, we have d dt partial of L with respect to theta dot. So now we're looking for theta dots in the Lagrangian, and we get m1L squared. Oh, I'm sorry. This will be d dt of, and then we take the partial with respect to theta dot, m1L squared theta dot plus m1L x dot cosine of theta. And when we take the derivative then, we get m1L squared theta double dot. And then we have to use the chain rule here, plus m1L x double dot cosine of theta minus m1L x dot theta dot cosine of theta. Sine theta. And the partial of L with respect to theta is going to be minus m1 L x dot theta dot sine theta and plus m1 g L sine theta. Okay, so the Euler-Lagrange equations, then, when we put all this together, so let's see, maybe I can shrink this down a little bit so we can see. Combining, I guess, we're going to combine those two equations into here, and we're going to get m1 plus m2 x double dot plus m1L theta double dot cosine of theta minus m1L theta dot squared sine theta, and then minus 0 is equal to the generalized forces on x, which is going to be F minus bx dot, and then combining these two into that equation gives m1L squared theta double dot plus m1L x double dot cosine of theta minus m1L x dot theta dot sine theta plus m1L x dot theta dot sine theta minus m1GL sine theta is equal to the generalized force, which is 0. Notice that that equation cancels with that equation, and then what we're going to do is we're going to combine the four terms that have double dots in them into a matrix. So we'll have m1 plus m2, and then x double dot theta double dot, and so this term is m1L cosine theta, and then the theta double dot gives us m1L squared, and the x double dot gives us m1L cosine theta. Again, notice that m is equal to m transpose, where m is that matrix, capital M. And then on the right-hand side, we'll have f minus bx dot plus m1L theta dot squared sine theta. And on the bottom equation, we have m1GL sine theta. Okay, so that's it. This equation is the equations of motion for the inverted pendulum.